All right, hi everyone. My name is Jeff Bezanson. I want to thank O'Reilly and Zaloni for putting this event on and inviting me. So I'm one of the creators of a programming language called Julia, which started in about 2009 to the public in 2012. Just out of curiosity, how many people have at least tried Julia or use it at all? Just a couple. OK, great. All right, that's good. So for everyone else, I'm going to start by just a really quick introduction to Julia and what it's about and what it looks like. I can't give a full intro to the language right now, but I'll just give you some flavor of what it's about. So here's an example of some of the kind of fancy syntax that we're capable of. So these expressions are all valid Julia code. So we like to have a kind of nice mathematical syntax that's very concise, very familiar to people who know applied math, statistics, and so on. So we like to have syntax like this. So you can, as you can see, we have support for these Unicode operators. And in all of the places you can enter Julia code, like at the prompt or in various editor modes or in the Jupyter notebook, we have support for doing LaTeX sequences. So you can just type, for example, \in tab, and it converts to the Unicode character for that operator. So you can write nice expressions like this. You can, so that the next one, you can see I'm doing sort of a local function. I can say let x approximately equal y equals something, and then in that block, you'll have that definition of that operator. So this is just a taste of the kind of syntax that you can do. So it's, this is really important to us, this nice readable mathematical syntax. What's behind it? The paradigm of the language is multiple dispatch, also sometimes known as generic functions. That basically means you define functions and the functions can have multiple definitions. The way we have done this, I like to think it's a way of fusing together many of the things that people need in languages into one simple feature. So if you know how this one feature works, you get all of this stuff that in most other languages is separate features, like templates in C++, overloading, classes, functions. To me, those are just sort of spuriously different, and they can really be combined into one mechanism, which is what we did, which I think gives you a lot of power while making the language a lot simpler. And the other thing about Julia that's a little bit different is that it's dynamically typed, so it's very much kind of a Lisp or Python family language. But we're very focused on static analysis. So we've designed the language to be amenable to various kinds of static type analysis so we can get better performance. And that's kind of one of the unique design combinations of the language. So just to give an example of how this paradigm works, I can define types. Like here, I've defined a point and a vector. And then I can just start writing out the definitions of how functions or operators are going to work on them. So in Julia, operators and functions are the same thing. So the plus operator is just a function called plus. So I can just say plus point vector gives a point, or I can also add two vectors and get a new vector. And you can just start stamping out these definitions. And there are really many really nice things about this. It's sort of fun to just stamp out whatever definitions you can think of for whatever types you've come up with. And since unlike class-based languages, the methods are outside the types, if you will, you can also add these things to other existing types. So if you want to add new functionality to other types, just go ahead and add the definitions. So I find this a really flexible, really extensible way to program that facilitates lots of nice things, and I'll show some examples of that. So here's an example of how this composability of this sort of works out. So the standard library has typical matrix and vector operations, but somebody made a package that defines unit quantities. So you can actually tag values as being of some SI unit. So I can say make a random matrix 2 by 2 and just multiply it by meters per second, and I get a meters per second matrix. And the way the type system works, it can basically lift the unit out of the array, so the unit's only stored once, and the array underneath has an efficient representation. And then I can also make a vector of seconds, and if I do matrix times vector, which is in the standard library, everything just sort of goes through, and I end up getting a vector of meters, like you might expect. So everything sort of composes together with this design very nicely. Another thing we do a lot of is we're very into linear algebra, partly owing to the origin of the project in MIT Applied Math Department. So it's kind of a tradition in technical computing languages in the Julia family, such as MATLAB, Mathematica, NumPy, R. Everybody writes wrappers for BLAS and LAPACK, which are sort of the workhorse linear algebra matrix libraries that have been around forever. They work really well, so everyone does that. But what often happens is people don't realize that there's actually a lot more functionality in LAPACK than is typically exposed in a lot of these systems. Because there's lots of functions in there for special matrix types. So not every matrix is what's known as a dense matrix, where you have a value at every point. Some matrices have special structure where they don't have as many values in them. And LAPACK is actually chock full of algorithms for all kinds of special matrix types. And those are not always so easy to get to. Usually, like in MATLAB, they only have the dense matrix algorithms. So we have a really big library in Julia of special matrix types. So like you can construct a symmetric tridiagonal matrix, for instance, where the only actual data is 2 vectors, but it behaves like that symmetric tridiagonal matrix, and then you can operate it on it as normal, and we'll just automatically pick the efficient algorithms for exploiting that structure. And we have a really big library of all this stuff. And in fact, that guy sitting right over there was a big reason for a lot of this. He's implemented a lot of it. And the other thing to note about these is these kinds of special structured matrices have non-trivial algebras. So this is part of why we want this very flexible definition system, so we can define the behavior of all of these based on whatever is correct, rather than based on what a particular type system forces you to do. So what has been happening? So this is a graph that summarizes the state of the world of Julia pretty well to me. This is the one I check up on regularly to see how we're doing. So this is for the past 2 years. Actually, exactly, it goes back to May 2014. Of the number of packages registered in our package manager. So you can see this is going up pretty nicely. We've just approached around 1,000 packages just recently. At this stage, we're seeing on average a small handful of packages registered every day, pretty much. More than 1 per day, usually. And you can see the green line there was the 2 stable releases ago release, so that's kind of leveled off now. People aren't targeting that anymore. It's pretty much dead, and the latest stable release, 0.4, and upcoming release, 0.5, is what everyone's working on, clearly. So, all right, so what is going on in those lines that are climbing up? What does that consist of? So in keeping with the theme of data for this event, I picked a few things that I see happening among those packages in the line that's going up, which is some experiments that are going on in the area of tabular data. And so one of the nice things about Julia is, since it's both very easy to write, but it's also very performant, it gives a lot of power to library developers. It's very easy to get a sophisticated library up and running and with good performance. You don't have to write any C or C++. If you know how to use Julia, and I think it's a pretty easy language, then you can write a really credible library just right away. And so this facilitates a lot of experimentation. So people have been doing all kinds of different approaches at different possible ways to handle tabular data, by which I mean things like the R data frame structure or pandas. So there are 4 projects here. So that top one is a basically strongly typed sort of schema-full tabular data structure. And then there's a new CSV reading package, which is pretty neat. It's by Jacob Quinn. It's really good. I actually just started trying it. It's really fast. The performance of it is pretty close to around Panda's CSV reading, which to me is kind of a gold standard. But it's written entirely in Julia, as all of these are. And then there's also somebody's working on a time series store. And then this last one is something I've been more involved in, which is this NANDSparse data structure, which I'll talk a little bit more about. So what these let you do, as I like to think of a benefit of this, is that of having a very flat architecture. Everything is just Julia all the way down. So you can work at these at whatever level makes sense. You can write an API, or the authors of these packages can provide an API that's very high level, like queries. Or if you want to just poke at the data structures and get the data in some other form, you can do that too. Or just write hand loops, scalar code, whatever you need to do on these things. So I'm going to show a little demo of one of these things that I happen to know a lot about, which is the NANDSparse one, just to show what this is like. And so this is actually very early stage work. This is very new. So I probably shouldn't really be showing this, but this event is about the future, so I figure why not? But something might go wrong. This is pretty early stage. So let's see what happens. So I'm just going to load a couple packages. And now I'm going to read a CSV file. This is just a random CSV file that I found on the internet that had some neat data in it. This data is about insurance on some real estate in Florida. So the CSV reader, what it naturally spits out is very much like an R data frame. It's basically a column data store structure that has some, let's see, it's got, so you can see the state over and over again is always Florida, and then there's the name of the county, and I think there's a latitude and longitude, and there's some dollar amounts in there, and so on. So it has all that data. And if you just want this, that's fine. You can do typical kinds of data frame operations on it, which is pretty old hat. But now what I'm going to do is I'm going to pluck out just a couple of columns because sometimes you want to think about this in a slightly different way. Like you might, so one of the columns in here is the total insured value, which is basically just the value of the property, that's the interesting part, right? Everyone loves to know how much stuff costs, right? That's the fun number. So you might just care about one number, and then you also might want to know certain other attributes of it. And then you might want to think about it basically like an array, where you have some coordinates in a space, and those coordinates include the geographic location and maybe some other properties about it. So you have those as your coordinates, and then you have finally the value is the data at the end of the day. So if you want to think about it that way, rather than as a kind of relational table, you can make one of these NANDSparse structures. So here I've just written a little line to pull out the columns I care about. So because it's a CSV file, dealing with it can be a bit awkward. So I just had to figure out which columns I cared about, and I just manually put in the numbers of the columns I wanted. So I picked the name of the county and the latitude and longitude, and then there's something that describes whether it's residential or commercial real estate, and then there's the construction, and then finally the dollar amount. So when I can just take all of those columns and construct this NANDSparse object from it. So I just gave it all of the columns, and you can see now it prints it this way. So now it's done a couple things. So now I have on the left, I've got tuples of coordinates basically, which map to the dollar amounts. So now this is sort of, it's the same data, it's a view of the same data, but it's kind of an opinionated view. It looks at it in a very particular way, where it says these are going to be my indexes, they're indexed, and then the value is on the right. And you can also notice that it's sorted. So it actually sorted this, that the indexes are all sorted lexicographically. And then I found one other fun thing to do, because it turned out someone made a package for Julia about currencies. So I loaded that too, and you can do this. This is the syntax it has. You can say I want to use USD. So that's the syntax for sort of importing dollars into your namespace. So I want to use dollars, and let me just make the additional refinement of just marking that last column is in dollars. So I can just map multiplication by dollars over the data, and now you see now it knows that all these numbers are actually US dollars. And this is this fun of composability, where someone else defines currencies, and I have this data and this other data structure, and I can use everything together. Plus, it's also efficient, which is always nice. So I find this cool, that if something is dollars, you can just tag it as dollars. And you can do this for indexes as well. The indexes here support anything that supports comparison. So you could also put, you could have dollars as your indexes, I believe, if that made sense. Now you can do, unsurprising kinds of operations. Like, so if I use this syntax, so this behaves like an array, right? It behaves like an n-dimensional array, where these things in the tuples are the coordinates, and these things are the values. So if you know anything about array programming, which many people do, many people are familiar with arrays, so they might want to work this way. You can index it, talking about the indexes. So here I've said I want everything except I want to select residential. And we can find the mean of that, which is about $324,000. Seems pretty reasonable. Or as compared to maybe the commercial, that's a lot. So the commercial mean looks like what is that? It's $12 million. So commercial real estate is more valuable, as you might expect. Right, so this is pretty neat. But now, so what's going on inside here is kind of the more interesting part, to me anyway. I mean, so So taking the mean of stuff about exhausts my knowledge of data analysis. You've seen pretty much everything I know about data, but I can go on about programming languages, fortunately. So let's look at this. So TIV is my array, which stands for total insured value. Let's look at what it is. So I can ask, what is the type of this? And it's this really long thing. So this is actually this is a Julia type, which basically gives you some structured information or like metadata, if you will, that's describing this. And so we can see, okay, so it's an NANDSparse object of US dollars. And then there's going to be a tuple here that describes the indexes. So the index space consists of a string, float, float, string, string. And then there's also types for the representation of the columns. So that's even fancier. So I'll show you what this is in a minute, but the columns of this have some kind of non-obvious representation, which is this pooled data array thing. And there's all kinds of other stuff in there. So this is sort of an intrinsic part of how Julia works, is it lets you take some data and construct this type or schema, if you will. You can construct it on the fly, right? Because everything about this is very data dependent, right? It depended on what we found in the CSV file. And it lets you construct this at runtime, make the structure for it, and behind the scenes, we will automatically specialize code for it. So I kind of suspect that a lot of the things that happen in the data world, a lot of data products out there, I suspect is really just somebody writing out by hand a specialization of something more abstract that a compiler could have generated. So that's kind of my goal, is to make that compiler instead of just constantly writing out every special case by hand. So I'll dig into a little bit more of the sophistication of this. So inside this, there are the indexes. So that's the index part. So that's sort of a part of this schema. It's everything about the indexes, not the data. And then if I go into the columns, so the first column is this. So let's look at what that looks like. It really just looks like an array of strings, right? But this, like often happens, there are many, many duplicates in here, which is really inefficient. Right, so what we've actually done is represented it not as a normal array, but as this pooled data array thing, which if we look into what's in there, so I can ask for what's in there using this function dump. So all right, that gave almost a little bit more than you want to know, honestly. Let's just try. So what's actually under there is there's this array refs, which, if you look at it, it's actually an array of bytes. So there aren't that many different distinct elements in this array, because it's just the number of counties in Florida or what have you. So there are not that many of them. There are less than 255 of them in this data set. So we can actually represent this as just actually a byte array. So underneath, the county is just represented by 1 byte of memory. And then it also just separately stores the pool of values. So it just stores each string once. Right, so there's this kind of very elaborate structure underneath this NANDSparse structure. So at every layer of abstraction, everything just keeps working, which I think is really cool. So you can have you have the overall NANDSparse structure, which is made of columns, and each of those columns can be specialized to hold the data that it has efficiently. And I want to take this farther. This is very much work in progress. I want to be able to support some other column types, like run length encoding would be another one that would be very interesting, right? Which is orthogonal to this, right? You can have few unique values and also run length encode, or do one or the other or both. So I think there's a lot of opportunity to have these kind of strongly typed, specially compressed in-memory representations, which we then will automatically specialize code over to get really efficient processing of these things. That's the hope anyway. Oh yeah, and of course it's fun to just, if you just look at the columns in a different order, you can just see it sorted a different way. So if I just pick, I could pick latitude first, and now it's sort of sorted by latitude. And you can see that the counties tend to kind of group together in a slightly different way. So that's kind of cool. So this is sort of a structure that we're developing that we hope will kind of exploit the underlying capabilities of the language to do some interesting data analysis. All right, so one of the reasons to do this, of course, so you saw the data in dollars. Julia has many, many other data types. The way the language works lends itself really well to defining number-like data types, or any kind of atomic kind of data type happens to be really easy to define, so people have defined lots of them. And this is a sampling. So you could use any of these in your, in your data frames or sparse arrays or what have you. And defining these, defining data types like this turns out to be actually pretty powerful. So we have, you can use any of these. Let's see. So some other, I'm just going to talk about a couple other new Julia packages that I think are interesting. So there's a group at Intel working on a package called Parallel Accelerator, where basically, I guess you could see it as they're impatient with the pace of development of our compiler, and they know optimizations that we don't know about and we don't know how to implement, but they do. So they have a package that lets you basically hook into the compiler and add their optimizations to Julia functions. And it works very simply. You can just annotate a function with this @acc macro, and it will just hook in there and basically tell us, run Intel's optimization passes on this thing. And it's very annoying. They're really good at this. It makes me look really bad. I like to think our compiler is pretty good, but but they like to make me look bad, and they have examples where you can get like 100x speed up. And this is the phenomenon that's sometimes referred to as ninja code, where if you know all the secrets of the Intel architecture and how to use the cache well and how to use threads well, you can just get these amazing speed ups. So they can just really, they can just get huge speed ups in some of these cases. It's very annoying. But we're talking to them, and we hope to eventually gradually integrate some of their optimizations into the normal compiler, so you don't have to use the package. You'll just get the performance by default. That would be the goal. There's this other work by this guy, Tim Bessard, who recently published a paper about a really nice GPU programming interface based in Julia, which I think is really impressive. GPUs are another area where you have kind of a disconnect. So there's, as soon as you need to go to the GPU, everything becomes really difficult, and you'd like a much more gradual path. It's a hard problem. There are many solutions out there. There are many ways to do it. I don't think we have a perfect answer. We don't have a silver bullet. But this one looks really neat to me because it lets you take, much like the Intel library, it lets you take a pretty normal Julia function, same syntax, same everything, but just say, I want to run this on the GPU. And underneath, it will just compile this to GPU code instead. So this is a really, really cool project, I think, this CUDA native package. For our part, so in the internals of the language, we also have, we have a release coming up, version 0.5. I expect it to be released in hopefully a month or two. So here's some new features. We have generator expressions. So we always had array comprehensions, but because we're very array-based, but they were specific to arrays. So now we have the general version, which is the same except without the array. You can just do this like Python-style generator syntax. We also have this dot syntax it's basically for map. You can take any function and apply it to every element of an array using this nice dot notation. And that's good because very often people who've used array environments like MATLAB, in MATLAB you can say sign of x, and if x is a vector, it'll just apply sign to everything. But that's kind of ad hoc, and it's a bit messy because you don't know, when is that going to happen? When does applying a function to a vector mean actually apply it to every element of it? It's a little bit haphazard. So this lets you be more explicit, but still be very concise about saying when you want to apply a function to every element of an array. We also have a much better code generation for higher order functions. So this arrow is a concise syntax for an anonymous function. It means take x and give back 2x. And so you can use a function like map and map that function over an array. And we will completely fully inline and specialize this. So you'll just get full performance for code like that. And there's also, for the first time in 0.5, we have shared memory threading support. So we've had distributed memory, distributed computing as part of the standard library pretty much since the beginning. But now we're going to have some experimental support for doing shared memory parallelism, which is really great because if you've seen the stuff that's available now, you can get single boxes with terabytes of RAM, actually. I saw recently, I think, something that's advertising 6 terabytes in one box. And if you do some quick mental math, if you think about a cluster with many nodes, say even maybe 100 nodes, if they have kind of a standard memory size of, 8 gigabytes, 16 gigabytes, it's still less. Like you can get more memory than that in a single box, right? So And I've talked to people who've said, you know, we don't run clusters. Why would you run a cluster if you can have one box with 6 terabytes of RAM and 100 processors, which you can get? So, you know, so I think shared memory could be a really big deal, and so we've started adding support for that. And also, one of the big pieces that's been missing in the Julia world is the tooling. So the tooling is finally growing up a little bit, and we have a debugger in the works. And I'll just show a little bit of what that looks like. So this is just in the normal Julia prompt. You can debug into something, and it'll show you code listing, and it'll highlight the line you're on. And you can ask for a backtrace, and it shows you where you are and shows you the values of variables, you know, just like you would expect. So we do have a debugger now, which is really exciting. And we also have Eclipse support. So, you know, every language has to support Eclipse. I'm not a big IDE person myself. I'm an Emacs and terminal kind of person. But, you know, you've got to have Eclipse support. That's just obligatory. So thankfully, we have it now. And we've also just very recently launched, so this logo in the top corner of my slide for Julia Computing, that is a company, actually. We offer support and services around Julia. And we've just very recently launched the Julia Professional Edition, which gives you a easy-to-install bundle, pre-configured. It has the Eclipse IDE, and there are a few add-ons available. So this is available now. We also have a 3rd edition of JuliaCon coming up. It's going to be at MIT, June 21 to 24. It's growing year over year. This year, I think we have about 60 talks, 2 tracks, and some pretty awesome keynote speakers. Thomas Sargent, Nobel laureate in economics, and Guy Steele. I'm very excited to hear from him. And Tim Holey, who's a neuroscientist and major Julia contributor. He was one of the big early adopters. And it's pretty amazing. The guy is he's a neuroscientist by day, but he works on Julia compiler almost as much as I do by night. I don't know how he does it, but it's pretty amazing. So that's it. Thank you very much.